Today we will conclude our discussion on recovery from failure, and first we will quickly summarize what we were discussing till now, and we will discuss some of the advanced features or some of the practical issues which are involved to make recovery more and more efficient. The basic issue of recovery was to maintain atomicity and consistency and to make sure that whatever commitment has been provided till now is maintained in spite of failures. For that we introduced the concept of a transaction, saying that a transaction is a program unit that reads required data items only once and writes them after updation only once, and a transaction always maintains database consistency. It is the onus of the user to write a transaction in such a way that database consistency is always maintained. So the database knows that a transaction is one consistent unit and it must be performed in full or none. That is the concept of a transaction, and in case of a failure midway, it has to be the effect of this transaction. If there is any partial effect of this transaction, that has to be undone and the transaction has to be re-executed. In order to understand the states of a transaction and the various places where a transaction may fail, we had the concept of a transaction being active when it is started and before all its statements are executed. It is said to be partially committed when all its statements are fully executed, and it is said to be committed when all the information which is supposed to be written from this transaction into the database are actually written into the database. That is when this the transaction is said to be committed. In between, in case of a failure, the transaction is said to be failed, aborted and restarted, and there is some operations which are to be done to undo some of the effects of this transaction, and those transactions which are reached committed state, for them also after, in case of a recovery, we have to take care of what we are going to do for them. For that we discussed what is called the log based recovery method, in which a log is maintained. Now this log can be maintained on the disk or can be maintained in the stable storage, in any stable storage. For the case of absolute security, in case of a disk crash or any other crash of that sort, the log is usually often maintained in a stable storage, and in terms of present day technology, it is all replicated disks. Replicated disks may be stored in one place, replicated disks may be stored in different places, is the concept of a stable storage, and a log may be kept on the stable storage in case of get recovered from failure. So for the time being, let us assume that in the simplest case the log is maintained in a stable storage, and a log consists of the simplest log consists of three statements. One is TI starts, which indicates when the transaction just prior to beginning of its execution. Before the first statement is executed, this TI starts is written onto the log into the stable storage, and we will assume in the initial stages that for every log record the corresponding block of that record is written into the stable storage. So we will assume when we say write T1 starts into log, that one is actually written out into a stable storage, and then during any data modification, wherever there is a write statement in the program corresponding to that transaction, we have that transaction number TI, the variable X, the disk data variable X, the old value and the new value. This is written into the stable storage. Now actually the data may not be written at that moment of time because of data buffering or virtual memory, but whenever the statement write is executed, this log record is written into the stable storage. And after the transaction commits, when a transaction commits means that all the logs corresponding to that transaction is written into the stable storage, which is effectively true, and all the data value which is supposed to be written onto the disk corresponding to this transaction is also written onto the disk. Into the disk means into the database, and after that only the TI commits log record is put into the stable storage. So this is how we have three options of log based recovery. We also discussed two types of database modification, one called the deferred database modification and the other called the immediate database modification. The deferred database modification defers the execution of all the write operations till the transaction partially commits. This means that whenever there is a write operation in any transaction Ti, that write operation is not immediately written onto the disk. The log corresponding to that write may be written onto the disk, but after the write is the actual writing of the value of the write into the disk is withheld till the transaction partially commits, that is till the last statement is executed. When the after the last statement is executed, only then the action of writing out into the disk occurs, and corresponding to each of the data which we said, it maintains a log, and as we will discuss a little later, that it does a redo of Ti in case of a failure. Now in case of a deferred database modification, since there is no modification which takes place in between before a transaction partially commits, in the log we need not write the old value, because the old value will continue to be maintained till the transaction partially commits, that is till the last statement of the transaction is executed. For example, we were discussing this simple two transactions, read A is assigned A minus 10, write A, read B is assigned B plus 10 and write B. And a transaction T1 which was read C is assigned C minus 100 and write C. Now when read A is executed, before read A is executed, T0 starts will be written into the log. Then A assigned A minus 10, nothing will happen. In deferred database modification, when write A is done, then T0 equal to A890 will be written onto the log, but the actual write will not take place. Then write for read B, nothing will happen, nothing will be written onto the log. B assigned B plus 10, then write B. Write B will not be executed, but T equal to B 510 will be written onto the log. Initially it was 500, now it will be 510. Initially this was 900, this will be 890. Now after write B is executed, this transaction partially commits. Now after this transaction partially commits, the actual effect of this write A and write B will be written onto the database disk. So A and B will now be written onto the database disk, and after A and B is actually written onto the database disk, the transaction will commit, and when the transaction commits, T0 commit log record will be written onto the stable storage. This is the sequence of deferred database modification. Similarly, before T1 starts will be written, then read C assigned C minus 100, write C. Whenever this happens, T1 C 1900, it was 2000, it will become 1900. This will be written into the log. This log record will be written into the stable storage. And after this, the transaction will partially commit. And when the transaction partially commits, after this, the actual write operation will take place into the disk. And after that actual write operation is completed onto the disk, T1 commits log record will be written onto the stable storage. This is the sequence of writing when T0 is executed after T1. Now the system may crash, that is the volatile storage or memory may crash and fail due to various reasons, and the log may be in several states when it crashes. So a log may be completely like this. The full log may have been written, that is after T1 partially commits, T1 fully commits, the power may go off, or there may be a system crash. In case of a failure in that, the recovery procedure will start. It will read the log record, and for any transaction which has got both Ti starts and Ti commits, in this case both of them are there for both T0 and T1, then it will execute these operations. What does it mean by execute these operations? It will write A 890 into the disk, for B it will write 510 into the disk, for C it will write 1900 into the disk. This is what we mean by the operation redo Ti. We actually need not re-execute Ti, but we will just redo the write operations on the disk. because we know what operations are to be written into the disk corresponding to that transaction. What is the intermediate executions, we need not bother, because the result of the executions which are actually to be written onto the disk is available with us. The other alternative is immediate database modification, and this allows database modifications to be output to the database while the transaction is still in active state, that is non-committed modification. Now what happens here? Let us see what happens here. Here, when read A is executed, before read A is executed, T0 starts is written, log record is written onto stable storage. A assigned A minus 10. When write A is done, T0 A 900 890 is first, this log record is written onto stable storage, and after this log record is written onto the stable storage, then this write operation is executed, in the sense that this write may actually take place into the disk. This is immediate database modification. This log record is written and then this write operation takes place. Read B, B assigned B plus 10, write B. Now before write B occurs, T0B 500 to 510, this is written. The old value has to be kept in the case of an immediate database modification. And after write B is executed, the transaction partially commits. After the transaction partially commits, actually write B must be fully written onto the disk, and after that the transaction will commit. When the transaction commits, T0 commit is written into the, this log record is written into the stable storage. Similarly for this one, first T1 starts, then T1C 2000 1900, and then T1 commits. First T1C 2000 1900 will be written, and then the value of C will be written into the disk. This will be written into the log, and this will be written into the disk, the database value. And after that the transaction will commit, and then T1 commits log record will be written. Now there is a slight difference between the recovery procedures of deferred database modification and immediate database modification. In the case of an immediate database modification, suppose we fail at the full instance, then the redo operation will be done. Suppose this one is the only one which is available, then redo operation will be done for this one, and we do not know T1 has started. But if we have something like this, then this will be done redone, that is 890 and 510 will be written onto this disk from the log using the log file, and then for T1, since only starts is there, it will have to be re-executed. But in the case of a situation like this, or a situation like this, where this log record is already there, we know due to immediate database modification, this value may have already been written onto the disk. Since this value may have already been written onto the disk and this transaction is not fully over, before restarting T0, we have to undo this. So we have to write back 900 into the disk. The undo operation writes the old value and the redo operation writes the new value. So for those transactions which have got both Ti and T0 starts and Ti starts and Ti commits in the stable storage of the log, for that the operation redo will be done, and for those which have got partial operations done, for that undo will be done. And these undo and redo are both idempotent, in the sense that if there is a failure during undo or during redo, then it can be done again and again. So this was what we discussed in the previous class, but due to we made some simplifying assumptions in the previous day because of our we said that every log record will be immediately written onto the stable storage. We said whenever there is a write statement in deferred database modification, it will wait till the end of the execution and then it will be written. And in the case of immediate database modification, that record will be immediately written onto the disk. But there are two issues here. One issue is that it is very expensive to write a log record each and every time into a stable storage. Firstly, writing into a stable storage is expensive, and then writing one record at a time, for which you have to actually write a whole block, is also expensive. So there are two things to speed up issues here. One is log record buffering, in which you do not write a log immediately into stable storage. You wait till a block is full and you write that block into the stable storage. Because you are just writing this log file is a sequential file. You are just writing one after another. So you wait till a block is full, and then at that point, so it is kept in the memory, and when a full block is ready, you write that block into the stable storage. You don't write anything else. So you don't write it at each and every point. So that is what is called log record buffering. So we will discuss log record buffering first. Then we will see what happens when virtual memory comes into the picture, the concept of database buffering. So in log record buffering, what we do is that we wait till we do not write each and every log immediately. That is, if we had to write T0 starts, this, at every time before priority execution, we just don't write T0 starts. We wait till one log block is full. The log records form a block, and once this block is full, we write that full block onto the stable storage. But there are some issues which have to be taken care of when you do log record buffering, because it is not as simple. So care has to be taken in the following three accounts. The first is, we must allow transaction Ti to enter commit state after Ti commit log record has been output to the stable storage. That is, if we say a transaction is committed and its Ti commit is in the memory, then it doesn't make sense, because if the power goes off and the system crashes, then this transaction has completed its execution. It may have written all the items into the database, and yet Ti commit will not be there in the log file. So the Ti commit log record must be output to stable storage before the transaction Ti enters actually is allowed to commit and complete. So we must either wait till that full block is written onto the stable storage, or we must force output that block onto the stable storage for that block which contains this Ti commit log record. The second point is, before Ti commit log record may be output to stable storage, all log records pertaining to Ti must have been output to stable storage. Now, before Ti commits, we may have in the memory, due to log record buffering, we may have several blocks in the memory and of log records, and we may not have outputted them into the stable storage yet. Now we cannot output Ti commit into the stable storage before outputting all the log records pertaining to Ti. So all log records pertaining to Ti must have been output to stable storage before Ti commit was done. But this was quite natural in our previous case when we were putting them one after another, because Ti commit was the last log record that was to be written. But now, since it may be in the memory, and there may be various such blocks in the memory, and it may not have been output to stable storage, you will wait for some time, maybe 2 or 3 blocks are full, then you will write them all onto stable storage. If you have a buffering algorithm like this, you must take care that this issue is also taken into account. And finally, before a block of data in main memory is output to disk, all log records pertaining to data in that block must have been output to stable storage. That is, suppose you have modified a block of data in a particular record, and you are doing a bit of database buffering as well. That is, you are writing a block of data into the disk. This is data corresponding to the database. So now, when you are writing a block of data back to the disk, unless that block has been modified, there is no point in writing it back to the disk. So when you are writing something back to the disk, it is obvious that that block has been modified. Now if in that block there are 4 or 5 records which have been modified, then in the normal case, since they have been modified and they are in the memory, when we use the simplistic idea that every log record will be immediately written onto stable storage, we were sure that the log record corresponding to that modified data is already in stable storage. But when we are using log record buffering, the log record corresponding to that data may still be in the memory and not yet have gone into stable storage. And due to your replacement policy, you may want to force output this block of data. So in order to make sure that consistency is maintained and recovery procedures can take place properly, we must be sure that all the log records which are now there in the memory corresponding to data for the block which is now to be output onto disk, these log records must first be put onto the stable storage or must be put into any storage wherever you are putting the log records, and only then you will output this data. So the output function must now be very carefully written in case of a log record buffering. You must take care, you must maintain pointers to the blocks corresponding, suppose there is some data in the database. You must maintain a pointer, or you must maintain information whether the log record for this data is in the memory, or you must determine that information somehow, or it has already been written. If it is still in the memory, it will have to be written or force output first that block, and then you will write this data. So though in general log record buffering tries to speed up the process, you must take care to maintain the consistency of the log file, because if the consistency of the log file is not maintained, there is no point in doing a recovery problem. This problem is even more aggravated or even more complex when you do database buffering as well. That is, now you are using the concept of a virtual memory in which you will write into the database only at certain points of time. That is, not when that disk is full, when that block is full, because you have brought a page from the memory or you have brought a block from the disk into the memory. You have maybe modified one or two places there. The concept of database buffering is that you have taken you want to modify a variable x which is there in the disk, in the database. Now for that you will input x. For input x you will input a block of that and you will modify it. Now that in database buffering, that block will remain in the memory because you may reuse that. And since you have a buffer area, that block will be written back into the disk either at the end of the session or when you require to replace this area of buffer due to input of some other block. So whenever this block will be remaining in the case of a database buffering. So now there is no order that since this data was written earlier, this data will be put into the disk earlier. This concept does not remain. Due to the replacement policy, anybody may be written for replaced back. The output operation is not strictly dependent on the sequence in which the data is modified. It may just be replaced due to the page replacement policy of the operating system or of the database management system if it does have a special replacement policy. So in that case, we have to again take care that the data which we have before we output that data, the log records and other information must also be put in properly. So when you combine database buffering with log buffering, you have a little more complex scenario, but if you manage it properly, you are bound to get a lot of speed up because each log record is small and writing into the disk is into a stable storage is quite expensive. So if you write one block at a time, you are going to save a lot of time. So the conditions which have to be taken care in such a situation is, if the input of block B2, this is input of database, if input of block B2 causes block B1 to be chosen for output, then the following steps have to be ensured. First, output to stable storage all log records pertaining to block B1. These are very logical steps, but we must take care of them. If every time any modification was done, log was to be written onto the log file into the stable storage, this is all right. This will always have to be maintained. But if the log buffering is done along with database buffering, then before we output block B1 into the disk from the memory, we must output to stable storage all log records pertaining to block B1. Because log must be output first and then the database modified. If you modify the database and then output the log, then there may be a crash between the time after you have modified the database and before you have output the log. So you must be sure that you do it in the proper sequence. So the sequence here is output to stable storage all log records pertaining to block B1, and then output the block B1 to disk, and then input B2 from disk to memory. So that is the whole sequence of operations that you have to perform in case of any output in database buffering or virtual memory concept that you may use. Now we come to another issue. The issue is like this. You have got a huge log file and you are maintaining starts, database modification, commits, starts, database modification, commits. Now we are sure that even in spite of database buffering or in spite of log buffering, we may have information that for a transaction Ti, it has started, its log records have been written, it has committed, all its database records have been updated. We know this, and there is a failure of the system in the sense that this is not a disk failure, this is a failure of the memory. Now it is quite futile to redo this operation because this operation has already been written onto the disk, isn't it? It is quite futile. It is only those operations for which you have got the full log. The operation which you undo and restart is fine, because for which you have got the partial log, you know it is in a partial state. But for an operation for which you have got a full log and you know the database operations have actually been done onto the disk, you need not redo. It is a wastage of time redoing because this whole log will be a huge set of data. You can well imagine in a railway reservation system or in any other system, at the end of the day, after 2 hours of booking, what the state of the log file will be. And it will take a lot of time to recover. We want to recover fast also. You need to recover or you need to redo an operation only when all the log records Ti starts, Ti commits is there, and you have information that, and you do not have information that all the data is being actually written onto the disk. That is the time you need to do the redo operation. So in order to speed up the recovery procedure, you use a concept called checkpointing. The checkpointing concept maintains, other than the log values Ti starts, Ti commits, Ti starts, Ti commits, it maintains the concept of something called a checkpoint. A checkpoint says that up to here, all the database elements have actually been written onto the disk. So you will have various Ti starts and value updations and Ti commits and checkpoints written. Now once you have a checkpoint written out here, you are sure that you do not have to do, you have to do only redo operations after the checkpoint, after the last checkpoint. So you check that whole log and you scan for the last checkpoint, and only after that checkpoint you do that. That is, all transactions which have got Ti start and Ti commit before the checkpoint, for that even redo operation need not be done. For all transactions which have got Ti start or Ti commit after, which have got both Ti start and Ti commit, only then you will do redo. And for them, Ti start and Ti commit is there after the database operation, after the checkpoint, any one of them. Ti start is there before checkpoint and Ti commit is there after checkpoint, or both Ti start and Ti commit is there after checkpoint, after the last checkpoint. Only for them you will do redo operation. For the others, you will just ignore. So you just look around the checkpoint and you determine those transactions from the last checkpoint for which you actually need to redo or undo. Undo means those transactions which have start and no commit, you undo them anyway, if you are in immediate database modification. And therefore database modification, nothing needs to be done. You just re-execute them. But once you have a checkpoint at a particular place, and you have a Ti starts and Ti commits for a particular transaction, such that the Ti starts is there before or after the transaction, after the checkpoint, and Ti commits is always there after the checkpoint, then you have to redo that operation. So this is a simple idea for which in the log you introduce another item which you write called checkpoint. So the checkpointing principle says, what are the steps that you have to do for a checkpointing? Before you write down the checkpoint, you have to output all log records currently residing in main memory to stable storage. Whatever log records are there in the memory, before you write down some, now you will not do the checkpointing at each and every time, you will do a checkpointing at certain intervals of time. So at certain intervals of time, in order to reduce your recovery procedure, say after 15 minutes, after 20 minutes, after 1 hour, it depends on the size of your log. So there will be a system related time in which you will start the process of checkpointing, and the process of checkpointing will do these. It will see all the log records in the main memory due to log record buffering and put them into stable storage. Whatever log records are there in the buffer will be put into stable storage immediately. Then all the modified buffer blocks will be moved on to disk. That is, all those buffer blocks which are modified in the database buffer will be moved on to disk. So all the update operations are over, completed. All log records and all update operations are completed. Now, and then you will write down a log record called checkpoint onto stable storage. So you will make sure before, so checkpointing is an operation which is done from time to time. So say after 1 hour you do checkpointing. When the checkpoint daemon is invoked, immediately these two actions take place. One is all log records are written onto the stable storage, and all the modified buffer blocks are first outputted back, and then checkpoint is written. So you are sure that whatever is there into the log, that up to that, whatever data was modified, that operation is completed. So for a transaction which has got both TI starts and TI commits before the checkpoint, its data is already there in the disk. In the log you may have a transaction for which TI starts is there, TI commits is not there, but checkpoint is written, because checkpoint is done at regular intervals of time. For that, if you fail, for that one you will do the undo operation, or you will restart it. And if you have a record for which after the last checkpoint you have got TI starts before the checkpoint is done, and after the checkpoint again due to the log record buffering some more records will be written from the log in the memory to the stable storage, you may have TI commits after that. For that one you will have to redo. So this helps to speed up the recovery procedure by doing a checkpointing at regular intervals of time. Now what do we do in case of a, these are all operations which we did in case of the failure of a memory. Instead of writing out this log into stable storage, we could have written this log into disk also. It is fine, because if the memory fails, the log is written into the disk. Now what do we do in case of a failure? You usually write the log into stable storage or in 2 or 3 places, one here and one maybe in a remote place. This is because of the problem of a disk crash. The whole system may crash due to something like an earthquake also. So in case of a disk crash, that is why this concept of writing logs into stable storage is always there. So in case of a disk crash, what do we do? That is, in between the whole disk crashes, there is a very simple thing that you can do. The simple thing is that you maintain a copy of the disk prior to the beginning of the session. The simplest thing which is done, you maintain a copy of the disk, whole data disk in a secondary storage, maybe in a tape or archival storage, prior to the beginning of a session, from where you have started the log, and then when the disk has crashed, you copy all this data into a new disk and you run the log on it from the beginning of that session. If the log is safe, in stable storage, then you just run the log on it, you will get all the modifications done. Here you have to take care that you are not, that checkpointing business is now of no use to you, because checkpointing means that you have written it onto the disk, but now the disk itself has crashed. So in spite of all checkpointing or anything, from the beginning of the session you will write everything onto the stable storage. So for this, a very simple idea may be employed. In many cases you may say that, okay, I would like to really keep not in the beginning of the session, but in between I would like to store everything which I have on the disk somewhere else. So that may be done in some very mission critical operations where the data itself is very, very important. But nowadays what happens is that this they try to have this dual copy drives in which you have disk data written in two places itself, and it is tolerant to failure in the sense that it is tolerant to failure of a single disk, but definitely it is not tolerant to failure to an earthquake. So in the case of a disk, so in between, like you do checkpointing, in between you do what is called a dump. You just write down the full disk somewhere else. And once you know you have written a dump, then from the dump onwards, whatever is there after the dump, and all those transactions which have started before the dump but have not completed prior to the dump, you from those transactions, or they may have started after the dump, for them you just do a redo operation. It's a very simple principle. So in the case of a disk crash, you output log the operations which you have to take care intermediate to write before you write down a dump. That is, a dump means all the disk is copied into a separate place. Before you do a dump, you must output all records currently. This is very similar to checkpointing or any other. The principle is same. If you know the principle, then these ideas become very logical. You output all log records currently in the main store to stable storage. You output all buffer blocks to disk as you did in checkpointing. You copy the contents of database to a stable storage. When you do dump, that means you must copy it onto stable storage, because otherwise it doesn't make sense. If you copy it onto another disk and it's thing like an earthquake, it doesn't make sense. So you copy it onto a remote storage. Stable storage here is something like this, whereas you expect it to be stable, and then you output the record dump. So just like checkpointing, when you know dump is there, in the case of a disk crash, from the last dump you just take it out, you archive it out, and then you make the log modifications. So this is how you have various recovery procedures in the case of failure, but these recovery procedures, as we have seen, are taken into account when concurrency is not there. That is, when there is concurrency as well as failure, then we have got other issues of atomicity, which we will first study when we study concurrency control, because we will see the concept of sharing. Here there is no concept of sharing of information, and there is no concept of parallelism in the sense of states being in partial execution and updating a same variable. So when you have got concurrency as well as failure, then you have got more complex methods of recovery, where checkpointing and other things will become more important, and we hope to see them in the future. But there are alternatives to log record buffering, to log based recovery scheme, and one of the alternatives which is proposed is called shadow paging. The shadow paging scheme is simple. It does not it is just a mechanism to take care of failure against memory, that is not failure against disk. So what you do is, you have got suppose this is the full disk area. It is defined into blocks or pages. So whenever you are taking for every page and whatever is there in a page, now these pages may not be in consecutive locations in the disk. So in order to know what is the set of pages, so this is the disk, and in order to know for a particular file what are the pages in the disk, for every file you have what is called a page table. This is very similar to the operating system ideas of file management. So using the page table, you look up and get the you will have the page table referring something like this. Now the concept of shadow paging is, for a page which is currently being used and brought from the disk to the memory, for that page you maintain what is called a shadow page. That is, in the disk you maintain two states of that page. One is, in spite of immediate modification or deferred modification, you maintain two states of the page. One state is the current page, that is the page which is the current state, and if there is any modification in the memory and it is written onto the disk immediately or after some time, that remains. The other is the shadow page, which is the state of the page before the transaction Ti was executing on that page. So, we have got what is called the current page table, and we have another page table called the shadow page table. Let us see initially what happens. Suppose this particular page is required to be input into memory. Whenever this particular page is required to be input into the memory, a new space is allocated, this page is copied here, and the current page table pointer is changed and put here, and the shadow page table pointer for this page is put here. And whatever modification that takes place on this page while a transaction T1 is going on is made here. If there is any crash before the transaction completes, then the shadow page is taken off and the transaction is restarted. There is no problem of undoing, there is no concept of an undo operation. Even in immediate database modification, there is no concept of an undo operation. Just the page is taken. Once the transaction completes, and we know this is the shadow page and this is the current page. Once the transaction completes, we make sure that this current page is used. Now when this page is brought back to the memory and this transaction completes, so this is the new state of the page. That information is maintained that this is now the new state of the page, and whenever this page is called back again, then this is again this is made the shadow page, and maybe some other location is made the current page. So whatever was the current page is made the shadow page, and another place is provided which becomes the current page, and whatever data is modified there, and as soon as the transaction completes, the current page becomes the same as the shadow page. So initially the current page is the same as the shadow page. Whenever there is an input operation which has to be taken place, that is a new current page is created, and when the transaction completes, the shadow page and current page are made identical. If there is a failure in between, then the shadow page is converted to the current page. Any questions?
We have 10 pages total memory space, and because of this shadow paging, will that mean that we have effectively only 5 pages? Because then we'll have 5
No, this shadow page is not, this shadow page table is not kept in the main memory, nor are these shadow pages kept in the main memory. This shadow page table, everything is kept in the disk, because if the power fails, if the volatile memory fails, we will lose the shadow page as well. The shadow page and the shadow page table is maintained on the disk. So corresponding to all the currently available blocks in the memory for which transactions are taking place, there is a shadow page for that block in the disk. The shadow page does not exist in the memory. The shadow page table and the shadow page exists in the disk, which said this is the state. The current page may exist in a partial state in the memory, and due to immediate modification and other things, it may exist also in a partial state in the disk. That is, for a page P, you have got a current page, you have made a current page, you have copied this into the memory. In the memory you have modified 3 records there, and you may have output these 3 records here, and that page may still exist in the memory, and some more modifications may have taken place in that page due to immediate database modification. So that shadow page reflects the state of the page which is available before the transaction took place, and it is there in the disk. Shadow page is also not there in stable storage. It is not, because logs are very small and they can be kept in stable storage. Nobody keeps a huge shadow page, the whole shadow page in stable storage. This is to quickly recover from failure against the problems of power failure or the problems of failure of volatile memory.
Does that mean that every read operation will create a shadow page?
Every read operation which, the question is, does that mean that every read operation creates a shadow page? Every read operation which results in input from the disk will create a shadow page. If a read operation results in input from the disk, it will create a shadow page. If that block is already available in the buffer, it will not create a shadow page. Now shadow paging has a problem. The problem is of fragmentation, because you are always moving it out here and there, moving a page here and there, and for a particular database file or a database record, for a database table, all of the records may initially be in a particular place, and due to this current page and shadow page movement, the whole record database may be fragmented, and that may cause a lot of inefficiency, because fragmentation does cause a lot of inefficiency, as we have seen in the case of a sequential file or an index sequential file. So shadow paging may be useful, and it actually depends on the application. A lot of analysis has to be done, but shadow paging is another concept which has been put to practical use, like the log-based recovery. So we have discussed in this series of lectures the basic log-based recovery scheme, and how we can do it, how we can maintain the concept of checkpointing and prevent loss of information. And this is a very crucial aspect of any database modification, and will come, this concept of atomicity and consistency will come into even greater prominence when we have concurrency, which we shall discuss later on. So the next topic which we shall discuss is concurrency control, where we shall see how sharing and accessing of shared data is done in a more secure manner.